give the climate physics-y talk for this morning. And I guess I've kind of changed the title a little bit, but it's the same as rephrased. And that's kind of what is the context of today's meeting in terms of climate change and what effects will it have. There we go. So I'll start off this talk with a little review of climate change itself, a very brief one, and then go on to the context of the future and what alternative energy means and their emissions imply for climate change. So to start off, we've got this question, what has driven recent climate change? And we all think carbon dioxide. But there are actually other things as well. And this, of course, complicates the whole picture. But we have, so carbon dioxide is the big one up here. But then there are things like methane as well, mainly from the agricultural industry. CFCs have had an effect. They're going down now, of course, because of the Montreal Protocol, but they're actually potent greenhouse gases as well. Then we've got this collection of things here, the aerosols, the sulfate aerosols, equivalent to smog. In the developing world, they're more or less, the developed world, they're more or less stable now or decreasing because, of course, past emissions controls. But in some places like China right now, they're increasing. I was in Beijing a few weeks ago and during their experiment, and it kind of frightened me to think what it must be like when they have all of the cars running. I guess they had an experiment where they only allowed half of the cars to run for 4 days, and it was pretty scary. But then there are also natural things as well, solar radiance, something that's not, the sun actually doesn't stay exactly the same brightness all the time. And there are also volcanoes going off all the time, big ones like Mount Pinatubo throw stuff up into the high atmosphere, which can stay there for about a year or so. So there's a whole pile of complicating things affecting climate change, the climate. And then, of course, there's the fact that what we actually see is the weather, which varies from day to day. There's all this internally generated variability going on. So what we end up is with something rather noisy. Now we can kind of smooth that out a little bit because it's kind of done this plot. Just look at this left-hand plot for the moment. If we just average according to decades, so the forcing, the response to carbon dioxide and some of the other things that we're looking at tend to happen on longer time scales, and that's kind of what's concerning us. So we can average out some of the noise, and then this is the observed change. We saw it just in the last talk as well, the black line there. And then we can run climate models. If we include all of the forcings that I was talking about there, all of these potential influences on the climate, and include them into our model, we get kind of this pink band here, which the observations follow rather closely. If we were just to include natural ones, we get the blue band. There's an anthropogenic effect here, most of which is greenhouse gases, and especially carbon dioxide. And we're now even getting to the point where we can do the same thing at continental scales. So here we've got Europe. There are certain complicated things. The black line seems to be following the pink band rather than the blue one. And in fact, in other continents, this signal is even stronger. How do we come up with this? Well, we have these, there are varying methods. You can use very simple models as well. In fact, they can work surprisingly well. But right now, in terms of if you want to get more local information out and things other than temperature, you have to resort to very complicated, computer-intensive dynamical models, which have the different aspects of the climate system there, the atmosphere, ocean, and you have radiation going back and forth, and also water and other things being exchanged between them. And you do this on a gridded globe, so you do it at each point in space, and you end up with something very complicated. But you can see here, this is from a climate model that you can run on your home PC, actually. Now, the advantage of computers becoming really fast these days. The climatefiction.net program, run out of Oxford, which you might have heard of. And you can see you've got cloud systems moving along here. Looks like there's a storm hitting England, so fairly realistic. And basically they generate weather, and you can do lots of experiments with them. Okay, so that's kind of the gist of what we know about what's happened with climate change and how we kind of work it out. But we can run these models on into the future as well. And so what happens when we do that? So we can do that and look at the 2020s. So we've got this here. This is the general pattern that you see. So this is how much the 2020s would differ from the last 10 years we've just experienced. And accelerated warming over the poles, especially the North Pole, and over the continents. It's just they can respond faster than the oceans. And here you get ice retreating, which really changes things dramatically. Okay, we can focus in on Europe, and this is a slightly more complicated plot, but I think the point about it is important. So here we have the months of the year, so you can just focus down on your favorite month, whichever one you were born in, and look at the gap between. Let's say take the red line here. So the spread between those two red lines is basically the range predicted, approximate 5th to 95th percentile of the range predicted by an international group of models, according to one business as usual emission scenario. So you can see that basically we're almost certain it's going to be warmer in the 2020s, according to this scenario, but exactly how warm is still a fair amount of uncertainty. The other thing is that, of course, this is one business as usual scenario. We actually don't know exactly, business as usual depends on what you think of in terms of how technology will develop and how the exchange of technologies will develop in the future. So there are other scenarios that people have come up with, which are the green and blue lines here. And the big thing is that the spread of these is almost identical. So the difference between assumptions you make on technologies, according to this business as usual model, don't make any difference up to the 2020s. You can even go to a really dramatic scenario where actually you assume that we stopped, that we did something rather funny in 2000 where we almost stopped emitting carbon dioxide, but we didn't quite, so that the level stayed constant. So in that case, we're staying constant at year 2000 levels of carbon dioxide concentrations. And it's a little bit cooler, you can see, but actually not too much. There's still mostly warming. The climate system takes a while to respond to things. And the black line is just if we just use one model looking at the scenario. So again, it's saying the same thing. So there's not really any model uncertainty here. There's not really any even emissions uncertainty. However, of course, we're not just concerned about the 2020s. Maybe you are in terms of the price of your home. But in the longer time scale, we're worried about the much more dramatic warming that might occur, say, by the 2080s. And in this case, you can see, so this is the graph we had beforehand, there's quite a strong difference here. It matters which scenario you're looking at. And this is just for the European area. So we're actually looking at a fairly small portion of the globe. You can see the commitment one, especially if we had held those emissions, or got rid of those emissions in 2000, we actually wouldn't have seen much warming. So it would have made a difference on the long term. Why is the world slow to react? For one thing, it takes a while for the carbon dioxide to come out of the atmosphere. The lifetime of carbon dioxide in the atmosphere is about 100 years, but of course the excess actually takes longer to come out. So if we have our emissions constant, year 2000 values, see an increase in black line there, and the cyan line here. If we actually cut our greenhouse gas emissions entirely, we see only a gradual decrease initially. And by about 2200, we're getting down to the levels we were seeing about the 1950s. So they stay a while in the atmosphere. The other thing is that most of the energy here, so this from the heating from these this greenhouse effect we're putting into the atmosphere and how it's being divided up into the different components of the climate system. And this is what's going into the atmosphere. So this is what's going into the warming that we're feeling. This is what's going into the ocean. So the oceans are actually a huge sink of heat and energy. Of course, it takes a lot of time for that to diffuse down into the deep ocean. So it acts kind of as a flywheel in everything we do. So when does mitigation actually make a difference? Well, by the 2020s, we're not seeing too much of a difference. But when we go out into the future, or the long-term future, 2100, say, we're starting to see a very big difference. This is just in terms of these business as usual scenarios. This is the commitment ones here, so ignore that. These other three ones are these business as usual scenarios. So they're actually not assuming any policy promoting non-polluting fuels, for instance. So we might be looking if we were to actually make a prediction, we might actually predict that this is perhaps a little more realistic because of what's happening in this room today and policy that might be going behind that. And then just a little bit on longer time scales, we can look at what goes on. These are rather dramatic experiments. So this is kind of showing going up to the year 3000 here. We still have carbon dioxide left in the atmosphere. We still have excess carbon dioxide. We still have excess warming. But exactly what level that warming got to depends very much on when we stopped and how quickly we stopped emitting carbon dioxide. So we were using the title of this conference, Sustainable High Innovation Fuels and Transport, mitigation kind of in general, if you will, or pollution control. Where do they come into the climate change issue? They don't matter in the short term, in 2020. They make potentially a huge difference in the long term. So we've got this difference of scales, which of course which has been the problem in many ways with the climate change issue, is that most of the damage is probably a much longer term affair. Although there's probably more on the shorter term. There are lots of uncertainties about how climate will change in the long term. Our models, you can take a model from one group which will predict something slightly different from, or for some things, dramatically different from a model from a different group. So we have uncertainty in terms of the shortcuts that are taken in making these models. One of the big things, of course, on the long term is that what carbon actually does in the natural world. Right now, it's being absorbed into the ocean. I think about half of what we emit gets dissolved into the ocean. But as the world warms, we might see peatlands and permafrost defrosting, and the methane that's held in them being emitted into the atmosphere. So the behavior of trees might change depending on carbon dioxide concentration and the temperature. So these are things that when you get to really a large amount of warming may become important. These are sorts of things that we probably don't want to gamble with. While we may not see too big a difference, only a few degrees, there's a possibility of a very large difference, and that's probably something we don't want to gamble with. They're quite plausible, some of these large changes, even if they're not probable. And so basically the bottom line of this then is everything that cuts down on emissions now, or in the next few years, can make these uncertainties much less important, because these things become important when we go to large temperatures, don't matter quite so much. And in many ways, when we go to if the warming is not going to be quite so big, then we won't worry about details so much either. Thank you.